Hello everyone. In this video, I'm going to prove the following statement in 3 different ways. What is meant by the first consecutive odd positive integers? Well, we're talking about 1, 3, 5, 7, etc. We are asked to prove that the first n terms of them is always going to be a perfect square. And what does this sum look like? Let us first call it S. It'll be 1 plus 3 plus 5. Now, how do we know where to stop? How do we know that we've got these n consecutive odd integers? Well, we notice the following. The first term, which is 1, can be written as 2 times 1 minus 1. The second term, which is 3, can be expressed as 2 times 2 minus 1. The third term as 2 times 3 minus 1, and so on. This means that the nth term must look like 2n minus 1. And this is our sum. There is also another way to check that these are n terms. We notice that this is an arithmetic progression, which means that we keep adding by a constant term, which is plus 2 in this case. So 1 plus 2 is 3, 3 plus 2 is 5, 5 plus 2 is 7, and so on. This number is called the common difference of the arithmetic progression, and let us represent it as d. In the case of the sum of an arithmetic progression, we have the following formula. In order to find the number of the terms, we calculate the last term minus the first term divided by d, and then we add 1 to the result. In our case here, the last term is 2n minus 1, the first term is 1, and the common difference is 2. So this becomes 2n minus 1, all of it over 2, plus 1. This becomes 2n minus 2 over 2 plus 1. Doing the calculation, we will end up with n. Alright, now we know our expression. Let us start with the first proof. The first proof I'm going to show you here is using geometry. Let us consider this square, whose side is n, and let us divide this square into smaller squares, each of side 1 unit. This is the first mini square, so we only have 1 square here. Here we have 3 more squares, so 3. Here we have 5 squares, so 5. Here we got 7 more squares. So I guess you got the pattern. In the next division, we'll get 9 squares, and so on, up to 2n minus 1 mini squares in the final layer. So what have we got here? First of all, we know that the total number of the mini squares inside this large square is simply n times n, and that's n squared. Let us, on the other hand, count how many mini squares do we have. We start with the first mini square, so we only have 1. Then in the second layer, we have 3 mini squares, so plus 3, then plus 5, and so on up to 2n minus 1. And this is our sum, which we already found, that is equal to n to the power of 2, which is of course a perfect square. And this is the first way of proof for which we used geometry. We continue with the second proof, so this is our sum, which means that 2s is equal to this sum plus itself. Now, since we're only adding here, we can regroup the terms as we like. I'm going to put together the very first term with the very last term, then the second term with the term before the last term. So if the last term is 2n minus 1, this means that the term before is 2n minus 3. We keep going the first way, so 5 will be added to 2n minus 5, all the way up to 2n minus 1 plus 1. This sums up to 2n, as well as this and this. This means that each pair of these sums is going to give us 2n, and it turns out that we have n copies of this 2n. This tells us that 2s is equal to 2n n times, and here you go, we proved that s is equal to n squared, and this is a perfect square. In the third way of the proof, I will use the fact that this is a sum of an arithmetic progression. Let us first recall what this sum looks like. So the sum of consecutive terms of an arithmetic progression is simply the first term plus the last term of the sum multiplied by the number of the terms and eventually divided by 2. If we apply it to our sum, then the first term is 1, the final term is 2n minus 1, multiplied by the number of terms, which we explained it's n, divided by 2. These ones cancel out. We get 2n squared divided by 2, and this is n squared, and again, it is a perfect square. And this is the third way of proof. This is actually a cool property because it allows us to perform the following sum very quickly without the need of a calculator. All you have to do in order to find the sum of the first n odd consecutive positive integers is to square their number, which is n squared. Let me show you an example. So the question here is to find the sum of the first 100 odd integers. It means I have to find the following sum: 1 plus 3 plus 5 plus etc. plus the last term, as we said before, is going to be 2n minus 1, that is 2 times 100 minus 1, which is 199. Now, even if I have a calculator, just entering these numbers is going to take time. However, if we use this property, we can simply say it is equal to n squared, and that's 100 to the power of 2, and it's 10,000. That's all for this video. Thank you for watching, and see you soon.